Hello everyone, I am Mana Samsika, currently doing my first year of Masters under the Department of IEECS. Today I am going to present on the topic of advanced optic sensors for structural health monitoring, pipeline flow detection, and ultrasonic inspection of structures. The contents of this presentation is divided into three, which is assignment 1, 2, and 3. On the first assignment, we'll be discussing on the introduction to fiber optic sensors, and second, we'll be going on with the pipeline flow detection using the acoustic sensor, and the third, we'll be moving on with the structural health monitoring with the help of the acoustic sensors. Introduction to optical fibers. A fiber optic sensor is a sensor that uses optical fiber as a sensing element or as a means of relaying signals from a remote sensors to electronics that processes the signals. Fibers have many uses in remote sensing. Depending on the application, fibers may be used because of its smaller size and no electrical power is needed at the remote location. By sensing the time delay as the light passes, the fiber through each sensor can be multiplexed along the length of the fiber. This fiber optic sensors works on the principle of fiber Bragg grating. A fiber Bragg grating is a segment of optical fiber that has a periodic variation in the refractive index of the fiber's core, and the variation creates a grating effect which is similar to the Bragg mirror. This is a typical fiber optic measurement system. Here, there is a light source which passes on through the focal lens that moves through the fiber optic sensors and which are detected by the photodetector. Here, a sensing element is placed between the focal lens and the optical fibers. The classification of fibers. The fiber optic sensors is classified into three types. First one is based on sensing or site location, and based on the second one is based on operating principle, and third one is based on distribution. Based on sensing and site location, we have two different types, which is intrinsic sensor, extrinsic sensor, and second one is the operating principle, which is based on intensity modulation, phase modulation, wavelength modulation, and frequency modulation. And finally, the distribution sensors can be classified into three types, which is Rayleigh, Raman, and Brownian distribution. And this is the wide classification of fiber optic sensors. The applications of sensors are divided into various different applications along the world. Some of the applications has been listed below. The first one is the temperature sensor, and the second one is the acoustic sensor. The third one is the train transducer sensors, and fourth one is the train identification system, and last one is the intrusion detection system. These applications are only on fiber optic sensors and not beyond any other source of applications. We'll be moving on to the second part of the assignment, which is acoustic sensor. An acoustic sensor is a device that detects and measures sound waves or vibrations in the medium of air, water, or solid. These sensors convert acoustic signals into electrical signals, which can be processed and analyzed. They are widely used in various applications such as medical, environmental, structural, and industrial. This is the operating principle of single and multi-mode. Here we have a different kind of configurations which can use to generate the multi-modes between two single modes. We can use different configurations. For example, we can use two short mode fibers and then splice it into a single mode, or we can even use the hollow fiber to exert the higher order modes. So operating principle is the same, but here we are working to investigate different types of configurations and to investigate what is the frequency range, its resolution, and its sensitivity. If you look at once the multimode fiber, once the light enter into the multimode fiber, the multimode fiber gets excited and the knock-off fiber on any other structure. So these multimode fibers will be exciting. So the number of modes depends on the V number and the multimode diameter of the fiber section. And then once the light coupled back to the single mode, then all the highlighted modes, Egan modes, linearly polarized Egan modes, will be coupled back into the second sum of splicer. So in this work, they have mainly focused on no-core fiber. So the no-core fiber highlighted modes are pretty sensitive to the external strain values. Now we'll be moving on to the vibrational sensor based on SMS fiber structure. Here is the laboratory demonstration of the vibrational sensors based on SMS fiber structure. They have used a very simple DFB laser at 1515 nanometers. And then they have used the SMS fiber sensors in case of multimode is a no core fiber. And then they have wrapped around the PZT transducer. The output signal mode will be coupled to the photo detector, which can convert the optical signal to the electrical signal. And then the strain changes and the spectral shift will be changing accordingly. Then they have modulated the output intensity. And to adjust the PZT, they have going to go to the pipeline flow monitoring. In this lab, they have characterized the sensing performance based on the function generator at different frequencies. If we apply 100 hertz of frequency, the fiber will experience a dynamic vibrations, and then the demodulated signals look pretty good at 100 hertz sinusoidal frequency. Here, the vibration sensing performance. If you look at the top left figure, this is the major FFTs up to 5 kilohertz, and then here is up to 400 kilohertz. You can see the normalized intensity and the wide range of frequencies. So, they have plotted a frequency versus the measurement of signal to noise ratio. This is around 100 hertz or something. The estimates are pretty low because the low frequency signal used to increase the frequency of the higher order which is applied to the PZT. So you can see the signal to noise ratio from 90 kilohertz up to almost 1.2 megahertz. So this can be measured with a wide range of frequencies, which is pretty good. And the MEMS based sensors will be limited to the bandwidth and expensive. But this one is the which is less than 2 kilohertz and which is high in signal to noise ratio. The wide range of frequency response can be seen, and they have the long term stability with the minimum drift, and they are also easy to install, and they are also provide the custom packaging, which is a continuous data logger software. The next one is the lab scale demonstration of the 2-inch diameter. This is based on the DFP laser. Here, the DFP laser is connected to three different SMS fibers, which is 1, 2, and 3. And directly, they have been connected to the DAQ. And the output is shown in the locations of 1, 2, 3. SMS fiber 1 is located in the location 1, and SMS fiber 2 is a location 2, and SMS fiber 3 is a location 3. The leak detection. So they have took 20 measurements at the same flow rate, and they have plotted the graph. The uncertainty is around less than 3 kilohertz, so it is pretty good and stable for all the flow. And then they have the right side figure, they have calculated the frequency and the amplitude of the root mean squared amplitude. Once they have done the flow induced vibration, by opening a valve, there is a valve in the pipe, so we can open the valve and then the water flows around. And then here they have fixed flow of valve in the pipe. So once we open the valve, the flow generates more vibrations because flow creates some disturbance in the vibration. So you can see pretty good amplitude changes. You can also calculate the FFT using the help of this leak detection. They are have high frequency measurement ranging from 1 to 1.2 megahertz. Right now, they have this measurement range. Now we are looking for the different configurations, like there is no core fiber. We can splice this photocrystonic fiber or the 3-core fiber based on millihertz resolution range. So we are also working on this leak detection system. Here the field demonstration, both water pipeline monitoring and leak detection. In future, they'll be doing with the water pipeline field demonstration and planning to apply the same sensor for natural gas pipeline monitoring. This is the third part of the presentation, where we'll be discussing about the guided waves for structural health monitoring, the acoustic operational instructions in optical fiber sensors for ultrasonic inspection of structures. The ultrasonic waves are excited from the actuator, and here they have SOLO lamp waves, which are measured with the sensors at a particular distance away from the slide. There are many challenges involved in this, which is cylindrical optical geometry and the small contact area. The detectors that are used are PZT, and the principle which is used is fiber bracketing. So remotely bonding FPG. In this, we have a composite pressurized tank application. The FPG is glued using the adhesive and connected to the lunable laser, the circulations, and then they are recorded directly. But the diagram there is the slight different, where rather than gluing the FPG to the structure in the green area is the glue. But the FPG is near the location which is called as remote bonding. The output signal amplitude of the direct remote bonding cases is not compared in this experiment. The most important is FPG is also unstrained in this experiment. The next one is acoustic mode propagation. Here there are three different modes, which is longitudinal mode, flexural mode, and horizontal modes. The LO1 mode is non-dispersive up to 10 to 15 MHz. The flexural modes will be decaying faster than that of the longitudinal modes, and then there are not detected by the FPG sensors. The propagational decay of the longitudinal mode is standardized silica mode, which has the fibers which is very close to the aluminum plates. The acoustic attenuation coefficient is the optical fiber, which is only one written with the FPG, which is glued at two different locations. The lamp waves will be coupled both at locations simultaneously, but arrives at FPG at different times. The optical fiber attenuation constant coefficient is denoted by 0.19 to its inverse. There are two different bonds, which is band 1 and band 2, which is matched using the matching gel. Why remote sensing bonding is beneficial? Since the FPG fiber is far away from the adhesive, the LO and AO lamp will be coupled to its LO1 mode. The distant arrival time of the FPG sensor for each mode are denoted by the red dotted lines. When the FPGs are directly bonded to the amplitude, they drop significantly. Here the AO mode propagates much slower than that of the change, and the longitudinal mode, as we move to the amplitude, the waves drop down. Due to the fact that they are propagating to the plate, the spreading effect takes place, creating a material attenuation. So now we'll be looking into the experiments. The several experiments have been conducted to the data which has cross-plotted in here, and the theoretical prediction attenuation is the line. It is well until h is equal to 250 nanometers. When a fiber is glued down, the drop happens, and here it is 80.5, which is located at the bottom. A large increase in signal is seen when we measure the longitudinal mode using the remote bonding. Then we have a fiber to plate coupling where the direction is unidirectional, and we only get the direction of the propagation in the fiber. But there is no back reflection. For plate to fiber coupling, it is bidirectional, and it is vice versa to the fiber to plate coupling. The result analysis shows the lamp wave is plate coupled to L01 traveling wave, which is optical fiber equally, which is forward and backward direction through a CA adhesive. The L01 modes coupled through adhesive tape show a directional coupling behavior, which can tune to the adhesive bonding condition to control the directional coupling. The acoustic coupling between the different fibers shows that the sensor networks for remote bonding is not just individual sensors to transfer acoustic signals. In dynamic acoustic transfer, we try to excite the resonance and from one fiber to other using the generation of fibers. Here we did both the solid standard signal and to the multimode up. The results of this graph shows that the coupling efficiency is a function of cross-sectional area, whether the fiber is hollow or solid. The coupling efficiency is sensitive to relative difference is cross-sectional areas between the output and the input fibers. So the conclusion, the advancement in fiber optic sensors represent a transformative approach to the monitoring and maintaining the critical infrastructure by leveraging the optical interactions within the fiber optic system. The technology helps in enhancing the efficiency, accuracy, and responsive of the remote monitoring in various sectors, from water management to the structural health inspection. The SMS fiber optic configuration and acoustic sensing capabilities offer significant benefits for the field applications. As this system evolves, they hold an immense potential to reduce the maintenance cost and improve the safety of the management essential infrastructure. The graph highlights the expanding role of the fiber acoustic sensors, especially in the sectors of requiring the continuous and real-time data to enhance the operational efficiency safety. This bar graph illustrates the future impact of fiber acoustic sensors across three different primary applications as listed below. Each bar represents a hypothetical impact scale on on 1 to 10, with the pipeline flow monitoring being the highest at 8, indicating a strong potential for advancement in this field. And the second is the structural health flow monitoring with a score of 7, reflecting the significant opportunities in the predictive maintenance and real world monitoring for infrastructure safety. And last is the ultrasonic inspection of structures, which is a score of 6, shows the promising but comparatively moderate potential for development. These are some of the references of my slides. Thank you.